thank you for having me here. My name is Chu Han Wu, and I'll be representing RWTH from Aachen, Germany. And the paper that I will be presenting is the Unified Framework for Mixed Reality Assisted Situational Adaptive Robotic Path Planning enabled by 5G network for deconstruction tasks. So basically, deconstruction tasks in 5G using mixed reality. So the first question is, why deconstruction tasks? So according to one of the annual report from Germany government, in the domain for demolition, renovation, and maintenance, so basically any sort of processes that deals with the removal of structure element from the building, there's a reported accident of 34.2% of the total and a whopping 43.2% of the total reported deaths. So it's clear to us which process that we should be focusing on right now for automation. And what's better than to remove the people from the deconstruction tasks by having a remote control system. And when we are talking about remote controls, of course, we have to go into networking. And for us, 5G networks is offered to us. And why 5G networks in comparison to 4G is that it has a much lower latency, it has a larger bandwidth, and it offers a functionality called network slicing. So why is lower latency preferable? In this case, we will be using ROS, which is a robotic operating system. And this lower latency allows us to communicate with the robot as close to real time as possible. And a larger bandwidth is necessary because we are working with, for example, RGBD cameras, we are working with 3D LiDAR sensors. And if anyone is working with 3D LiDAR sensors, it creates a point cloud data that is immense for every frame, every second, and this cannot be achieved with 4G, and we need 5G in order to upload all of the data into our edge server in order for some sort of human detection or pre-processing. Yeah, and that's why larger bandwidth is necessary for us. And for network slicing, you can understand this as more of like a task distribution within the 5G networks. And for when we have remote planning, we need to have a visualization for us. And this can be done using Unity engine for mixed reality. And for our experimental setup, we will be running this in a 5G industry campus Europe, which is known as 5G ISE as well. And for us, the tower crane acts as a transmission tower, and this is positioned centrally and usually at an elevated position on the construction site. So these Omni antennas are a bit special because they are rotational neutral to the maneuvering of the crane, which means that no matter it's going on the 180-degree clockwise or anti-clockwise, it wouldn't affect any of the performance of the antennas. And the implementation for the AR is that we will be using inverse kinematic for the end effector, and a URDF file for the robot are imported into Unity. And this URDF file is very important for us because it allows us to save the meshes in hierarchical order in order for the inverse kinematic to work. And the communication between ROS and Unity is established using this TCP connection. And for the augmented reality, you'll be using Vuforia engine or AR core. And here comes the more interesting part, which is the communication of the 5G of the AR application with the machine itself. So the machines are connected to different 5G networks via P2P VPN. And the AR application that is described previously is built and installed on an Android tablet. And this doesn't have to be an Android tablet. It can be a HoloLens, for example, any sort of augmented reality devices or HMD. And the robot model is anchored on an image target. And then the path of the end effector can be visualized and planned using the AR applications so that you can see that what are the spaces that we are using, is there any collisions when we are deploying the construction machines. And all of these messages are then sent to the computer that are connected to the same network for calculations and encrypted before sending to the computer. that are connected to another network. So this is our result. So you have see on the left is the Unity server endpoint, and then the ROS for visualization of how is the communication, and the AR application. So on the blue dots, we see we can manipulate the path that the robots will be taking, and also for the red path is the path that you'll be taking as well. And yeah, and then for the latency test, which is very important to us, is that we'll be running ICMP, UDP, and TCP tests respectively. And we are running ROS at a frequency of 10, 50, and 100 for each of the tests. And surprisingly, there's not much effect in terms of the average latency. All of them has about roughly 30 milliseconds. So we can conclude that even at running at 100 frequencies, at 100 first, it wouldn't matter too much, which means that we can have a lot more bandwidth for the robot to run. And so for the outlook and potential is that it can have a digital twin of the construction site, because we can control the robot and can see what is happening with the robot at real time, close to real time, which is about 30 milliseconds. And according to one of the white papers by Ericsson Network, the real time for that requirement is about 10 milliseconds, but we are close to that. And for ROS2 specifically, we have this domain ID specification, which means that we can apply more than one robots. We can have 1, 2, 3, and the network is able to support that. And we can visualize each of the robot using our AR applications for controlling, visualization, and to know what's the real-time updates of what's happening on the robot itself. And one of the future work that we would like to have is actually the modeling of an ontology. So ontology is basically the linkage of the messages and how does the function of the machine works. So for example, in the graph or the figure, you can see like even for machine A is two machines of the same one or different one. As a matter of fact, we can have different protocols, and all of these can communicate with each other, and it can know what it should be done at certain situations. So it can eliminate any sort of human interaction. So this is another step forward to automation in our case, and also for semantic zoning. For example, we can visualize what are the zones that are being used if we have an ontology model for situation for zones and shared spaces for safety purposes as well. And I'd like to acknowledge the project that's financing this project.
Thanks a lot.